All right. Welcome back to Lecture 6. This is Part B, so the second part of a two-parter. We're going to continue with some more examples of differentiation. Let's take a look at this one. So let's find f of x for the function f of x equals the square root of x. Okay, so let's find f prime of x, and then once we've found the derivative, let's find the slope of f at x equals 1 and x equals 4. Okay. So we'll just kind of emphasize that we can do such things with the derivative. So first we got to find the derivative. Now, in the next lecture, we'll get into how to find derivatives efficiently. All right, we'll get into that in the next lecture. But right now, the only way we know how to find derivatives is using kind of the machinery of the limit definition that we had. So that's what we're doing. But just know, I remember when I took calculus, and my teacher didn't tell me ahead of time that, hey, you're gonna. There will be easier methods for finding derivatives. I remember being like sort of dumbstruck by the sheer laborious nature of finding derivatives in this manner. And so I was much relieved when I discovered that, but I'm letting you know in advance so that you don't have to feel the same frustration. Just know that there are nice, easy ways to find many of the derivatives of interest. But this is the hard way to do it, and we're going to stick with that way just for a couple more examples so that we can, kind of drill it into our brains how this thing really works. Okay, so f of x plus delta x minus f of x, all divided by delta x. That's the definition of the derivative. And so plugging in the specific function, we would have x plus delta x, the square root of that, minus the square root of x, divided by delta x. Okay. Now, sometimes, as I'm sure you'll agree, math is tricky, and tricks will exist that you maybe had never even conceived of. Because you might look at this and say, how in the world am I ever going to evaluate this limit with that delta x in the denominator? Well, we're going to have to get rid of it somehow, aren't we? And so what we can do is we can do an old trick from algebra. Whenever you have something in the denominator that you don't like, try multiplying top and bottom by something else. Okay, and so what we're going to do is multiply the top and the bottom by x plus delta x plus the square root of x. Okay, and we can do that, right, because this factor that we're multiplying on here is equal to 1, right? Irregardless of what all those quantities are, if it's a ratio of the same thing. So same thing over the same thing equals 1, right? So we can do this kind of thing. And when we do this, our denominator no longer has the same problems. And so let's just do, let's multiply out the top, right? So x plus delta x times x plus delta x is going to give you an x plus delta x, right? These are square roots. You multiply the two square roots together. It's like squaring the square root, and you undo it. And then you're going to have two terms that are plus or minus the square root of x times x plus delta x. And so those will go away, and then you're left with minus x up here. Okay, and then in the denominator, let's just write it like this for now. Right, so just kind of putting them in there together. Now, if you look at that numerator, the x and the minus x undo each other. And so what I have is basically a delta x in the top, and then conveniently I have a delta x times this other factor here in the denominator. Like so, right? Now, obviously, these are going to cancel, and this was my chief source of concern, and that is going away now, which is nice. So I have the limit as delta x goes to 0 of 1 divided by, now I just have this term, which I can evaluate this limit at x plus delta x, that's a square root, plus square root of x. Okay, so what happens when delta x gets infinitely small? What happens when delta x approaches 0? Well, this piece under the root goes to 0, and so what I'm left with is 1 over 2 times the square root of x, right? Because I've got a square root of x plus something that's becoming 0, and so this piece of it here goes to 0, but you still have the x, and then I have square root of x plus square root of x, just 2 times square root of x. Okay, so the derivative is 1 over 2 times the square root of x. Okay, and so I could find the slopes, right? So my first slope I was interested in was at x equals 1, and so that's just going to be equal to f prime of 1, which is 1 over 2 times the square root of 1, which is a half. Okay, and the other one that I was interested in was at 4, x equals 4, so that's just f prime of 4, which is 1 over 2 times the square root of 4, which is 1/4. Okay. So let's take a look at this function and see how it looks. Right? So you might remember what the square root of x looks like as a function. I'm going to try to draw it reasonably well. Yeah, so it kind of goes like this. And so here at, so this is 1, it goes through there, it goes through 0, 0. And then out here at 2, 3, 4, it should be equal to 2. So I'll just kind of try to draw this reasonably well. Kind of looks like this. Okay, now this doesn't ever turn back on itself, so it kind of heads off, right? And it grows, you know, without bound, but slower than normal. And so this would be the point 1, 1. This would be the point 4, 2. Okay, so what we've said is that at the slope here at 1, you know, basically the slope here is a half, and then the slope here is a 1/4. Okay, so these slopes are kind of dying off. Now, what you would discover as we kind of move closer and closer to the point 0, what we would discover is that the slope of the tangent lines will increase, and they'll increase rapidly until the tangent line is basically vertical at x equals 0. Okay. So, very nice. Now, the reason you get such a crazy, issue here with the denominator is that, I mean, this is a f of x equals the square root of x has, limitations with its domain, right? Clearly, x can't be a negative number, so x is greater than or equal to 0 at all times, or that's the domain of the function. So that kind of can lead the derivative calculation to being a little bit screwy. So let's do another example. Let's talk through. Let's just kind of do something a little more applied. So what's the slope of the tangent line at x equals 1/2 for y equals 2 over x? Okay, so kind of trying to get into some different notation here. So dy dx, okay, that's equal to the derivative with respect to x of 2 over x, just kind of plugging a bunch of stuff in. Well, that's going to be equal to the limit as delta x goes to 0 of, now here it's, well, let me make sure to write it here. F of x plus delta x minus f of x over delta x. This one is a little bit weirder because the x is in the denominator, right? So you want to be careful when you're plugging this all in. So f of x plus delta x is going to be 2 divided by x plus delta x. okay, like so. Okay, and then minus f of x would be 2 over x, and then delta x down below here. And so we can, I think probably the best place to start would be to combine these numerators and sort of resolve this fraction within a fraction situation. So limit as delta x goes to 0. Now we're going to have to get a common denominator here, so let's make it 2x minus 2 times x plus delta x, and then the common denominator will be x times x plus delta x, and then the whole thing is over delta x, let's not forget. Okay, and let's and remember this is like delta x over 1, so it'll be the limit as delta x goes to 0, and now it'll really be 2x minus 2 times x plus delta x divided by this thing. Okay, and then times 1 over delta x, so just kind of being explicit about what we're doing here. And so we gotta, kind of combine all of these things together. So limit delta x goes to 0, 2x minus 2 times x plus delta x all over x times delta x times x plus delta x. Okay. All right, so that's kind of the long way around, but just making sure that, because I know people should be ready for calculus, but a lot of times some of this, like algebra, can be a little hairy. I just want to make sure that going through each of the steps very explicitly so people don't have any hang-ups over exactly how things are being calculated. So now up top here, let's just clean this up a little more. So I've got basically 2x minus 2x minus 2 delta x. All right. And down below, I've got the same. Okay, so obviously up top, the 2x and the minus 2x go away, right? And so I'm left with negative 2 delta x, all divided by this stuff again. So I know that, you may be looking at this and just like feeling exasperated by the length of the calculation. So obviously I'm not cutting any corners. I'm doing every step explicitly on here, which you don't have to do. The other thing to notice here is that, as I said, this is like a temporary calculation for us. We're not going to be calculating derivatives like this for long. So just take your time with this. Recognize that there's only a finite number of these that you're going to end up doing in your life, and just indulge yourself, and don't be afraid to write the same denominator 3 times without changing it. Just the key here is not speed. The key is accuracy. Okay, and so what can we do? Well, we can cancel these delta x's, and that's key, right? Because if you don't cancel the delta x, then when this delta x goes to 0, it brings everything with it, and that's the problem. So we get the limit as delta x goes to 0 of negative 2 divided by x times x plus delta x. Okay, and now we take the limit. Basically, this term is going to drop out. It's going to become inconsequentially small. And so you get negative 2 over x squared. All right. So dy dx equals negative 2 over x squared. And remember, our initial ask was to identify the slope of the tangent line at x equals 1/2. And so we now have the derivative function, and we can just evaluate the derivative function at x equals 1/2. And so we could say there's different ways to write this, but you can evaluate it like this. So it's equal to negative 2 divided by 1/2 squared. So that's negative 2 over 1/4, which, again, doing the math, negative 2 over 1 times 4 over 1 would be negative 8. So the slope of the tangent line of the function y equals 2 over x is equal to negative 8. All right, good. So that is another example. Now our definition of the derivative, right? There's a lot of different ways to define this. The definition we've been running with is f prime of c is equal to the limit as f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta of x. So that's been the kind of the definition we've been working with. Now, at times, there are other definitions that you can use. One particularly handy definition goes like this. So it's basically just a change in the way that we denote some of these things. So let's imagine we have our function here, and we've got our 2 points just like before. This is the point C, and now this time we're going to name this point x. Okay, so this point here is C comma f of C, and this point up here is x comma f of x. Okay, so these naturally are C and x evaluated within a function, and so this horizontal delta x can be thought of as x minus c, and this vertical delta y can be thought of as f of x minus f of c, right? So it's just this distance, is this height, which would be your f of x over here, and it minus this height, which is your f of c. Okay, so hopefully you can see that this is literally just a different way of kind of labeling things, right? It's not like a totally different definition. It's a different way of sort of articulating the concept and just using different notation. And so what this would lead to, this leads to this labeling leads to a definition f prime of c equals the limit as x approaches c of what's the change in y, delta y over delta x, and so delta y is f of x minus f of c, and of course delta x is now x minus c. Right, so this is just another way of saying let's bring x closer to c, bring this point closer, and let's calculate the tangent line, the slope of the tangent line as these things get closer and closer. And in fact, let's take the limit as x approaches c, which means x sort of disappears into c, becomes arbitrarily close to c. And this is just a different way of articulating that whole process. Okay, so this form has its uses. So this form is useful when thinking about continuity and differentiability. Which is what we want to go into next. We want to talk about specifically continuity, differentiability, and their relationship. Right, so does one guarantee the other? Does the lack of one mean the other is not true? Like, what's the implication? How are the two related? Okay, so we're going to get into that, and that's kind of the motivating reason for introducing this kind of updated definition. Now, when you think about this definition, notice that the existence of this limit requires that the left and right hand side limits for the same point C exist and are equal. Okay, so specifically we would need the limit as x approaches c from the left of f of x minus f of c over x minus c. That needs to exist and be equal to the limit as x approaches c from the other side of the same ratio, right? The same function here. So these two need to exist and be equal, and that's something that we need to explicitly say with regard to this definition. Now, the previous definition, right, a delta x was going to 0 and intuitively, like the distance, the change in x is kind of thought to be a positive quantity, and so we didn't have to explicitly state this, but here it's important. Right, here it makes sense and is important to state, and in particular, we're going to use these to examine situations where continuity maybe doesn't exist, and where potentially continuity does exist, but differentiability doesn't exist, that kind of stuff, right? And so we'll take into account the left and right hand limits for some of the examples that we're going to look at. So let's start by looking at an example of what happens if we attempt to calculate a derivative at a point where we do not have continuity. Okay, so what happens if we want to try to calculate a derivative at a discontinuity? Okay, so let's consider a function we've seen in the past. Let's consider f of x equals the greatest integer function. Okay, now remember what this one looked like. I'll draw it again. Okay, this is like a step function, right? So at every integer, the thing would step up. Okay, so for example, it would exist here, and then it would jump up, and there'd be a hole, and then it would jump up, and then there'd be another hole. And the same thing was true here, down below. Right? And so on. Basically, we have non-removable discontinuities at every integer value. Everything in between the integers, just fine. There's continuity there, but we have these discontinuous jumps. Okay? So what happens when we attempt to evaluate the derivative at particular integer values? So let's take like x equals 0. For example, let's calculate the left-hand limit first. So the limit as x approaches 0 from the left of, remember, it's f of x minus f of 0 over x minus 0. Okay, now remember x is approaching 0 here, so what happens? Let's write this here. Let's put the actual function in there. So this would be the greatest integer value minus 0, okay, divided by x minus 0. I'll just put x. Okay, so what happens here? Well, in the numerator, so we're approaching 0 from the left-hand side, right? So the function isn't defined at 0, but we're just getting close to 0. And so what happens to the numerator? Well, we plug this in, right? You end up with a 0 up top, right? And so the value of the limit goes to basically 0 divided by x approaching 0, right? So it becomes infinite. What happens from the other side? The limit as x approaches 0 from the right-hand side. Okay, same function here. Okay, so if we're approaching 0 from the right-hand side, what happens? You get a 1, right? So here we can see that basically the two limits do not produce the same value. Okay, right? So this is going to be like x over x, right? So it all cancels out and you get a 1, right? So it works there. Here, x is stuck in this negative as we're approaching the absolute, this guy stays negative, but this guy's going to 0, so the whole thing actually goes to negative infinity, right? And so here you've got basically two of these guys that just don't agree. And so that means that the limit as x approaches 0 of f of x minus f of 0 over x minus 0 does not exist. right? So this would be what defines the derivative, right? So obviously the derivative at 0 does not exist either, okay? And so in this case, the function is not continuous at x equals 0, hence the jump discontinuity there. And so we can see that it is also not differentiable, okay? So it is not differentiable because it is not continuous. Okay, all right. However, it is, so what we've just seen is that not continuous in this case implied not differentiable. Okay, so that's one side. So this is just a specific example. Let's see what happens. And let's see what happens when we have what we'll see is that continuity does not imply differentiability, right? So it is possible for a function to be continuous and yet not differentiable. Okay, so let's talk about an example that kind of gives us that scenario. And the function that we'll use here is f of x equals the absolute value of x minus 2. Right, so remembering what this looks like. So here's 1, here's 2, 3. Okay, so what this does is it comes down here and it goes like this. Okay, so this is the absolute value function, right? So one of the things that you can probably tell by looking at this, like if you try to imagine what the tangent line is going to do here, it's very easy obviously to see what the tangent line is going to do on this region of the function and also on this region of the function. But what happens here? What happens at x equals 2? Does the tangent line look like this? Does it look like this? Does it look like this? How do we know? Right, so there appear to be options. And so I think what we'll discover here is that this is an example of a function that's continuous. There are no gaps, no discontinuities, but it's a function that is not differentiable. And so we can see this specifically at x equals 2 if we try to find f prime of 2. Okay, so f prime of 2 would be equal to the limit as x approaches 2. We're going to check it from the left and right, and specifically of x minus 2 minus 0 over x minus 2. Okay, and well, so remember this here is f of 2, right? So f of 2 is 0. That's where that came from. But what you can see is that this limit here would evaluate down to being a -1. So if we're approaching 2 from the left side, you can clearly see that the slope here, the slope of this section is -1, and that's indeed what you get with the left-hand limit. We don't want to do it that way. So what happens with the right-hand limit? Well, as we're coming down this direction, right? So x is, above 2, then what you're going to find is that this guy here is going to evaluate to so this guy here would be a positive value, whereas here it was negative. The denominator was negative, and that's what produced the -1. Here it's positive. The numerator is obviously also positive, and so you get a positive over a positive, and so you get the right-hand limit is equal to 1. Right, so the two are not equal. Okay, and so that's sort of where the differentiability, the lack of differentiability comes from. You can't calculate an actual derivative at this point. So f prime of 2 does not exist. Okay, even though this function is perfectly continuous here. There's no gaps, there's no hole in the domain, there's no non-removable discontinuity, no asymptote, nothing weird. It's just that the curve, the idea of a tangent line here just is simply not workable, right? There's no way that a unique tangent line could exist at this point. And it bears out in the definition when you try to actually calculate the derivative. Okay, and so even though we haven't really proved this, this is kind of the way it works. Differentiability. Differentiable implies continuity. Right? If a function is differentiable at a given point, then the function must also be continuous at that point. Right? So f prime of 2 exists implies f is continuous at x equals 2. Basically is what that's saying. Now the reverse is not the case, right? So continuity does not imply differentiable. And that's what we just saw with our previous example. We saw this with f of x equals x minus 2 up to the value. Okay, so we saw a counter example where we had a continuous function that wasn't differentiable. So a function may be continuous and still not differentiable, yet if it is differentiable, it must be continuous. Okay, there it is. So I think that will be that's a good place to end our introduction to differentiation. The next videos will, the next lecture will be, we'll get deeper into differentiation. We'll start uncovering some of the basic differentiation rules. We'll start with examples of how you might identify differentiation rules, and then we'll just start like stockpiling them, start building them up. So we will see you then.